two implementations of exactly the same operation. Same inputs, same outputs, same maths. The second one does more arithmetic, about 13% more floating point operations. It runs 5.5 times faster. Not 5%, 5.5 times while doing more work. And it isn't an approximation, it computes exactly the same answer, not a cheaper estimate of it. So either the extra arithmetic is free, or arithmetic was never what you were paying for. It's the second one. And once you see what you were paying for, a lot of things about running these models stop being mysterious. Here's the thing worth your next 12 minutes. Flash attention is not an AI algorithm. It's a memory hierarchy optimization that happens to have been applied to attention. The transformation at its heart is cache blocking, chopping a computation into pieces sized to fit fast memory. High-performance computing has done this since the 1980s. It's why the fast matrix multiply libraries on your machine are structured the way they are. The AI field spent about 5 years trying to make attention cheaper by doing less arithmetic, sparse attention, low-rank approximations, a whole literature of them. Many of those made the operation count go down and the wall clock time not move at all. They were optimizing the wrong quantity. By the end of this, you'll be able to say precisely why attention is memory-bound rather than compute-bound. What I/O-aware actually means as a design principle. How you tile an operation whose normalization depends on the whole row, which is the part that looks impossible, and why the result is provably close to optimal rather than merely clever. Start with the machine because everything follows from it. This is the memory hierarchy on an A100, and these are the numbers from the paper. At the bottom, the machine's main memory, over a terabyte of it, reachable at about 12.8 gigabytes per second. Above that, the GPU's own high-bandwidth memory, 40 gigabytes at roughly 1.5 terabytes per second. That's the 40 gigabyte card on the spec sheet. When people say a model doesn't fit, this is what it doesn't fit in. And on chip, the SRAM, about 20 megabytes total at an estimated 19 terabytes per second. Look at the two ratios because the whole video is in them. SRAM has roughly 13 times the bandwidth, and it is roughly 2,000 times smaller. That's the trade the hardware hands you. Enormous speed, almost no room. One detail, and it's the one most explanations get wrong. That 20 megabytes isn't one pool. It's 192 kilobytes on each of 108 streaming multiprocessors. Multiply it out, and you get your 20 megabytes, but no single piece of work sees all of it. A block of work gets something on the order of 100 kilobytes. 100 kilobytes is the real budget. Hold onto that number. It's what sets the tile size later. Now the operation. Attention scores every position against every other position, so for a sequence of length n you get an n by n matrix of scores. Video 2 covered why. Here's what nobody shows you, how big that thing is in bytes. Take the configuration the paper benchmarks. Sequence length 1024, 16 heads, batch size 64. 1024 squared is just over 1 million entries. Times 16 heads, times 64 sequences in the batch, that's about 1.07 billion numbers. At 2 bytes each and half precision, the score matrix is a little over 2 gigabytes. 2 gigabytes against a working budget of 100 kilobytes. It was never going to fit, so the standard implementation does the only thing it can. It writes that matrix out to the 40 gigabyte memory and reads it back whenever it needs it. And it needs it constantly. Score the pairs, write the matrix. Read it back to apply the causal mask, write it. Read it back for the softmax, write it. Read it for dropout, write it. Read it once more to multiply by the values. And in training, keep it because the backward pass needs it. Every one of those arrows moves 2 gigabytes across a bus. The measured total for one forward and backward pass on that configuration is 40.3 gigabytes of traffic. Now put the hardware engineer's question to it. How much arithmetic do you do per byte moved? That ratio is called arithmetic intensity, and it decides everything. The score matrix multiply is fine. For each entry you do work proportional to the head dimension, around 64 multiply accumulates per element. That's a compute-bound operation. Good. But the softmax, you read a number, you exponentiate it, you write a number. Order one arithmetic operation per element moved. The mask, read, compare, write. Dropout, read, multiply, write. Those passes do essentially no arithmetic. They are pure memory traffic over a 2 GB array several times. So the expensive part of attention isn't the matrix, multiplies everyone counts. It's the cheap element-wise operations sitting on top of an array too big for the fast memory. So how do you stop paying that? The obvious first move is kernel fusion. Instead of 4 separate passes, each reading and writing the matrix, fuse mask, softmax, and dropout into one pass. Read once, write once. That's a genuine win, and it's what people did. But it doesn't solve it. You still materialize the full n by n matrix once, and in training, you still have to write it to memory anyway because the backward pass needs it. The paper says this directly. Saving intermediates for the backward pass is what limits naive fusion. The obvious second move, the one the field actually took, is to make the matrix smaller. Sparse attention, low-rank approximation, compute fewer of the n-squared entries. Fewer operations should be faster. It largely wasn't. That's the paper's opening complaint. These methods reduce the operation count but frequently show no wall clock speedup at all. Of course they don't. You cut the arithmetic, and the arithmetic wasn't the bill. You also gave up model quality to do it. So a different question. Not how do I do less work, how do I do the same work in a different order so the working set fits in fast memory? That question has a well-known answer, and it isn't from machine learning. Naive matrix multiply, 3 nested loops. For every output element, you stream a whole row and a whole column. If the matrices don't fit in cache, everything you loaded gets evicted before you reuse it, so you fetch the same data over and over. The fix isn't fewer multiplications. It's the same multiplications, reordered. Chop the matrices into tiles sized to fit the cache. Load a tile. Do every operation that touches it while it's resident. Then move on. Identical arithmetic, identical result, a fraction of the traffic. Cut the tile to fit the cache, and the traffic drops by a factor that grows with the square root of the cache size. That's loop tiling, cache blocking. Every serious numerical library does it. Now apply it to attention. Split the queries into row blocks. Split the keys and values into column blocks. Load one block of keys and values into SRAM. Loop over query blocks. Compute the small block of scores on chip. Use it immediately. Throw it away. The big matrix is never written anywhere. It never exists. Except you can't do this. Because of the softmax. To normalize a row, you need 2 things reduced over the entire row. The maximum, which you subtract for numerical stability so the exponentials don't overflow, and the sum of the exponentials, which you divide by. You're holding one block. You don't know the row's maximum. A later block might contain something larger. You don't know the sum. You've only seen part of it. You cannot normalize, and until you normalize, you don't have an answer to accumulate. That's the real reason nobody had done this. Tiling a matrix multiply is textbook. The softmax couples the whole row and appears to forbid it. So instead, normalize with the wrong number and fix it afterwards. Process the first block. Keep 2 running numbers per row, the largest score seen so far, and the running sum of exponentials measured relative to that maximum. Accumulate a partial output using them. The second block arrives, and it contains a larger score. So every exponential you've accumulated is relative to a maximum that's now too small, all of them wrong. But look at how they're wrong. Each one is off by the exponential of the old maximum minus the new maximum. That quantity doesn't depend on the score. It's the same factor for every term in the row. Which means you can apply it retroactively. Multiply the running sum by it. Multiply the accumulated output by it. Both are now expressed relative to the new maximum, as if you'd known it all along. Add the new block's contribution. Continue. At the very end, divide by the final running sum. That's the whole trick, and here's why it works. Exponentials turn a shift into a multiplication. A change in the maximum doesn't invalidate your partial results, it just scales them, uniformly. You never needed the whole row in advance. You needed the ability to rescale after the fact, and the exponential hands you that for free. One problem left. The backward pass needs the score matrix to compute gradients, and you just spent the whole video refusing to store it. The obvious answer, store it, is the thing you're avoiding, so instead, recompute it. Keep the output and those two running statistics per row. 2 numbers per row is linear in sequence length, not quadratic. In the backward pass, rebuild each block of scores on chip from the blocks you still have. That's selective gradient checkpointing, and it costs more arithmetic. Which is your cold open. The flop count went up. The traffic went down by roughly 9 times. The clock went down by 5.5. Stated generally, and this is the result that makes it more than a good engineering hack. Let n be the sequence length, d the head dimension, and m the size of the fast memory. Standard attention touches high bandwidth memory a number of times that grows with n times d, plus n squared. The n squared term is the matrix you materialize. Flash attention touches it a number of times proportional to n squared, times d squared, divided by m. Divide one by the other, and the win is the fast memory size divided by the square of the head dimension. Head dimension is typically 64 to 128, so d squared is a few thousand to 16,000. Against roughly 100 kilobytes of usable SRAM, that's a factor of several to a few tens. Measured, on real configurations, the paper reports up to 9 times fewer memory accesses. Notice what's in that expression. Bigger fast memory, less traffic. The algorithm's cost is parameterized by a hardware quantity. That's what I/O-aware means, and it's why this is an architecture story rather than a math story. And the block size falls straight out of it. You size the tile by dividing the available SRAM by the head dimension. That's it. That is precisely what you do when you size a DMA burst against a scratchpad, and it's the same calculation. One more result, and it's the strongest claim in the paper. They prove a lower bound. Across a range of fast memory sizes, no exact attention algorithm can do asymptotically better on memory accesses. So this isn't just faster. Within that model, it's optimal. There is no clever version waiting to be found. Back to the cold open. The measured figures, GPT-2 medium, sequence length 1024 on an A100. Standard attention, 66.6 billion floating point operations, 40.3 gigabytes of memory traffic, 41.7 milliseconds. Flash attention, 75.2 billion operations, more 4.4 gigabytes of traffic, 7.3 milliseconds. 13% more arithmetic, 1/9 the traffic, 5.5 times faster. The whole video is in that row. 3 more things you can now explain. Why long context arrived when it did. Memory footprint goes from quadratic to linear, up to 20 times more efficient than exact baselines. Sequences that ran the card out of memory now fit. The paper trains on sequence length 16,000 and, with the block sparse variant, 64,000, producing the first transformer to beat chance on a benchmark that had defeated every previous attempt. Why the approximate attention literature mostly lost. Those methods traded model quality for fewer operations. Flash attention gave up nothing, changed no model definition, produced identical perplexity, and beat them on the clock. When the exact method is also the fast method, the approximation has nothing left to sell. Why there's a flash attention 2 at all. Version 1 reached only 25 to 40% of the machine's theoretical peak throughput. Fix the memory traffic and you become compute-bound, and then the next bottleneck surfaces, which turned out to be how work is partitioned across thread blocks and warps. Version 2 rebalances that and reaches 50 to 73%, roughly twice as fast again. Remove one bottleneck, expose the next. Anyone who has optimized anything knows that rhythm. What I simplified, and what's genuinely uncertain. Exact needs care. It means no approximation is made, the same function is computed, not an estimate. It does not mean bit-identical output. You're summing in a different order, and floating point addition isn't associative, so results can differ in the last bits. The paper reports matching perplexity. It doesn't claim bitwise equality. The streaming softmax isn't theirs. Online softmax normalization was published in 2018, and a 2021 paper showed self-attention doesn't need quadratic memory. The contribution here is combining that with tiling, proving the I/O bound, and critically, writing the fused kernel that turns it into wall clock speedup. Prior work had the maths without the machine. I showed the forward pass and one loop order. The backward pass is considerably more involved than recompute it. Version 2 also swaps the loop nesting and parallelizes differently. I showed version 1 because it derives more cleanly. I drew the full square. With causal masking, entire blocks above the diagonal are masked out and real kernels skip them, which is close to a factor of 2 I didn't mention. Every number here is an A100 from the 2022 paper. Current hardware differs. The SRAM bandwidth figure in particular is described in the paper as an estimate, not a datasheet value. Flash attention 3 targets Hopper specifically, asynchrony, low precision, and reports figures in a different league entirely. The principle survives all of it, the constants don't. The tiling only works because attention is one big matrix operation with no memory of position. Which raises the obvious question. If the mechanism can't tell a sentence from a shuffle of itself, how does the model know word order at all? That's next.